Okay, question 1. We got a piece of fishing line. It could hang 23.8 kilograms of mass before it breaks. If you use the same fishing line to swing a rock with a low mass 20 or 2.85 in a circle of radius 0.791 meters on a frictionless flat table, how fast, linear speed, could you spin it before it breaks? Okay, so this is getting to be a little more complicated questions because we're getting up in the chapters. So it's really a two-parter. It tells us one scenario and then it tells us another scenario. So in the first scenario, it's going to hang from a mass. And the mass is going to be 23.8 kilograms. Okay, and that's the maximum it can do before breaking. So what that's going to tell us is that this will have an Fg equal to mg, and there'll be some max tension. Okay, there'll be some max tension in the line. The second part of it says that if you spin this rock in a circle on a frictionless table, how fast could you possibly spin it before it breaks? Okay, so in this case, we're going to go around and around in a circle of a radius r. That r would be equal to 0.791. V is what we're looking for, okay, because this is linear speed. V is what we're going to be looking for there. This m is different because now it's a rock, so it's 2.85 kilograms. And as we spin around, we'll see what happens with that rock. So first, I want to use T max because that will tell me over here how fast I can spin. The reason it's going to tell me is because of centripetal force. Okay, so if we sum up all the forces, we'll get the centripetal force being overall, because it's traveling with a constant velocity in a circle. Circular motion gives us our centripetal force, which we know is, well, I can put it here, that's fine, mv squared over r. Now, what is keeping this centripetal force in play? Well, the tension is what's keeping that rock from flying off. So this is equal to the tension. And if you want, you can write tension pointing inward. That would be the tension, and the centripetal force points the same direction, but on the other side of the equal sign points towards the center. It's the overall force. So in here we have that T, and we want to spin it as fast as we can before it breaks. So I want T max to be here. M doesn't have a max, but V would have a max, and that's what we're looking for. Okay, so I'm going to use this T max to plug into this T max, and then from there I should be able to solve for whatever the velocity is. Okay, so first one, let's figure out what the T max is. So these I know are in equilibrium, which means some of the forces in the y are 0, which means that T minus Fg, which means T is equal to Fg. Fg is equal to mg. Mg is equal to 23.8 times 9.8. So our T max, 23.8 times 9.8. Our T max is 233.24 newtons. I'm going to take that T max, I'm going to plug it in over here. So we'll have 233.24 newtons. That is equal to this scenario's mass is 2.85. V is what we're solving for, so I'm going to have V squared. And over R. R was given 0.791. Okay, so now I just need to solve for V squared. So multiply by the denominator on both sides, get rid of this, so this times 0.791 divided by 2.85, and then finally take a square root. So I'm going to take that, multiply it, divide it, and then finally square root it. Okay. If I do that, you should end up with a V max of around 8.05, or we can just say 8, which is what we got for our answer.